Welcome to this video on energy and work. Yesterday in class you saw the uses of kinetic energy and gravitational potential energy, and today we're going to talk a little bit about how we actually calculate the amounts. So we should remember that kinetic energy is the energy of moving, of motion. The skater had kinetic energy when they were moving down the ramp, but not when they were stationary on the ramp. Gravitational potential energy is the energy of being off the ground. Right, so being off the ground, or the energy of height is kind of how I want to think about that. And so it makes sense that each of these things will depend on these specific objects. So when we talk about kinetic energy being the energy of motion, that means it's going to depend on the velocity. So velocity is going to be a major part of our equation for kinetic energy. In fact, kinetic energy is also dependent on the mass, because an object that has more mass also has a lot of energy. So the result is that our kinetic energy is given by the equation 1/2 m times v squared. Now, because it's the energy of motion, the v then ends up having a bigger proportion of change with regard to the overall kinetic energy. If you doubled mass and doubled velocity, the doubling part of velocity would be a much stronger, or a much bigger increase in our overall kinetic energy. So kinetic energy is given by 1/2 mv squared. Again, our mass should be in units of kilograms, and our velocity should be in units of meters per second. The result is a unit called the kilogram meter squared per second squared, which is also known as a joule. Gravitational potential energy, on the other hand, is the energy of being off the ground, or the energy of height. Again, it's going to depend on our mass. We found that if you increase the mass, you increase the energy overall. We also found that as you increase the height, you increase energy, and hopefully you found in our secondary lab that if you increase the gravitational pull, the gravity constant, then you also increased your gravitational potential energy. So the equation for gravitational potential energy is m times g times h. Mass times gravity times height, where m, again, is going to be in kilograms, g is going to be in meters per second squared, and height is in meters. The result is, again, a unit of kilograms meters squared per second squared, which is, again, the joule. Notice that our joules over here and our joules right here are in fact the same unit, which will be very useful a little bit later on in this presentation. So let's take a look at a practice problem for kinetic energy. We have a car of this mass, and it's moving at 25 meters per second, and I'm asking you how much kinetic energy does it have at the start. Well, we should remind ourselves that the equation for kinetic energy is 1/2 mv squared. So go ahead and pause the video for a second and figure out these three questions. Welcome back. If our kinetic energy is 1/2 mv squared, then this is 1/2 1470 times 25 squared. The result is the value of approximately 4.6 times 10 to the 5th joules. After coming to rest, how much kinetic energy does the car have? Well, that one's pretty straightforward. Again, if we understand that k is equal to 1/2 mv squared, if our v is equal to 0, then we have no kinetic energy. So 0 joules. Not OJ, but 0 joules. That's how much kinetic energy we have there, because we are stopped. The third question, what is the change in kinetic energy and where did that go? Well, if this is our final kinetic energy and this is our initial kinetic energy, then our change, delta k, is given by k final minus k initial, which is equal to negative 4.6 times 10 to the 5th joules. Negative 4.6 times 10 to the 5th joules. And where did it go? Well, it went into the brakes. It went into heating up the brakes. If you think about the physical situation, we have a brake that clamps down on the wheel there as it spins, and as that brake slows us down, it heats up. And so that energy is lost to the thermal energy in the brake. Here's a practice problem for gravitational potential energy. We've got a bowling ball of mass 5 kilograms that we're lifting from here up to here. And I'm asking you to tell me how much gravitational potential energy it has initially when compared to the ground, how much it has finally when it's up at your shoulder as compared to the ground, and what was the increase and what caused that increase. So take a second, pause the video, figure that out, and then come right back. And welcome back. So if we're trying to figure out gravitational potential energy, UG is mgh. So for this case, UG initial is going to be equal to mg times h initial. The reason I can do that is because h is the only thing that changes here. Mass is the same and gravity is the same. So when we plug in our values, we've got 5 times 9.8 times the initial height of 0.61, and the result is our initial gravitational potential energy of 29.9 joules. That's UG initial. Our UG final is given by mgh final. And so as we plug in those numbers, 5 times 9.8 times 1.12 gives us a value of 54.88 joules. And this is my UG final. So the increase in gravitational potential energy, I went from 29.9 up to 54.88. So that's an increase, delta UG equal to 24.99 joules. And where did that come from? Well, the thing that was lifting the bowling ball was you. So you used energy to lift the bowling ball from where it was originally at 0.61 meters up to its maximum height of 1.12 meters. And where did that energy come from? Well, that came from you eating something earlier today. And where did that energy come from? Well, then we get down a very long rabbit hole. Now, you found this idea of energy conservation yesterday in class, but I wanted to reiterate it a little bit. The idea of energy conservation is that energy in any given situation can neither be created nor destroyed. It has to go somewhere. Now, if we deal with things that are not stealing or leaching forces, things like friction, things like air resistance, then our total amount of mechanical energy, that's kinetic plus potential, will be constant no matter what. So if we take a look on the left-hand side here, we're actually going to ignore this right-hand side, don't worry about it. If we take a look at the left-hand side, if we start out at some ground level, so we start out, we throw a ball from the very bottom of its path, the ground level, we start out with just kinetic energy. As we go through, as we go up, at the top we have potential energy then. You can see that here. So our kinetic energy changed to potential energy, and then as it fell back down, it changed back to kinetic energy. Now the thing that I want you to keep in mind here, or look at here, is that if I were to draw a line across the top here, all of those bar graphs would be the same height. So the energy that was originally just kinetic, all of it got transformed into potential, and then all of that got transformed back into kinetic later on once it got back to its location. If I were to look at the ball maybe right here, go ahead and draw a short bar graph of what that might look like. Let's say the ball is falling down. What would the bar graph look like between kinetic and potential at that point? We'll say it's somewhere around halfway. Go ahead, pause it, and take a look. And as you come back, we should see that kinetic energy and potential energy both have some amount of our energy. So if it's about half, they're probably going to each be about half. And the total, if this is our amount here, the total then should add up to however much we had before, if this is our total. And you saw that yesterday in the lab. And so the idea is no matter what kind of energy you have, the initial amount of energy that you have is equal to your final amount of energy in the absence of forces like friction. Really the only force that we'll deal with that doesn't conserve energy in this class is friction or air resistance. Those two forces are essentially the same. So some sort of friction force, that's the only thing that we will have that takes away energy from our system. There are other things that can add it, but takes away energy, friction. So the idea of energy conservation says that in the absence of friction, our energy that we have at the start is equal to our energy that we have at the end. Energy initial equals energy final. That's the whole idea behind energy conservation. Whatever you had for initial energy, that's equal to whatever you had for final energy. And what do we do to figure that out? Well, that's where energy expressions come into play. So we have to figure out what kinds of energy are at each point in time and set them equal initially and finally. So hang on just a second, I have a practice problem here. Let's see. Here it is. Nope, not this one. Oh, right, it's down. Here we are. So during a hurricane, a large tree limb of mass 22 kilograms falls down from an initial height of 13.3 meters to the roof of a building 6.0 meters off the ground. So if we're asked to find how much energy it has when it strikes the roof, and then the speed of the branch when it hits the roof, we have to use the idea of energy conservation. So the first thing I would like you to do is at this point, we'll call this our initial point and this our final point. At this point, write an expression at the initial point, write an expression for the kinds of energy that are present, just like we did in the practice problems at the end of class last time, the kinds of energy that are present at that point in time. Go ahead and do that, and then do the same thing for the final energy. Welcome back. So initially, we have our energy initial equal to just gravitational potential energy. And then at the end, we are both off the ground and we are also moving, so our energy final is going to be equal to kinetic plus potential energy. So initially, our energy is just gravitational potential, and in the end, our energy is gravitational potential and kinetic. So to figure out our kinetic energy, we have to say that our energy initial is equal to our energy final. And so then we can say that initially our UG initial is going to equal UG final plus my kinetic energy final. And so how am I going to figure this out? Well, initially I have mgh, right? Because remember, mgh is my gravitational potential energy, and kinetic energy is 1/2 mv squared. So initially I have mgh1, which is going to be 13.3 meters off the ground times 9.8 times 22 kilograms, and that gives me an initial energy of, let's see, 2,867 joules of energy. In the end, then, we have the same concept here, except now we're only 6 meters off the ground. And so the result is that in the end, we have 1,293 joules of potential energy. And we have some amount of kinetic energy left. Now remember, energy must be conserved, so any energy that we lost in gravitational potential energy has to have gone into kinetic energy. So on the left-hand side of our equation, we have 2,867 joules. On the right-hand side of our equation, we have 1,293 joules. So the difference between those is going to be how much is left for our kinetic energy. So the kinetic energy then that's left over is equal to 1,574 joules. So 1,574 joules of kinetic energy. That's how much energy we lost that was all in potential energy, that now some of it has gone to kinetic energy. So we started with just potential energy. You can see down here, we started with just potential energy, and we had no kinetic energy to start, right? This is 0 kinetic energy. And we ended with some potential energy and some kinetic. So this number here, this was 2,867. This number was 1,293, and so the result is this number must be 1,574. This bar graph concept here is a really good way to keep track of our energies. If you start with potential and kinetic on both sides, then you can say that your kinetic is 0 at certain points of time, and you can then use that to figure out exactly how much energy you have locked up in different forms. So remember, if we're trying to find the speed, our kinetic energy final is equal to 1,574 joules. And so that's equal to 1/2 m times v squared, which equals 1,574. So the result is that our velocity, or our speed, as we hit the roof is about 12 meters per second, 11.9 meters per second. Pretty fast for a tree branch to hit at 11.9 meters per second. So that roof is probably not in great form. Okay, now the last concept that we have to talk about in this video is the concept of work. And work happens when you exert a force on something over some amount of distance. So work is not really defined as, but is indicated by a force applied over a distance. And the purpose of work changes energy. Work changes energy. So when we have work done on an object, that object's energy is changed. Sometimes we can do work to change the potential energy of an object. Sometimes we can do work to change the kinetic energy of an object. If we are not changing the potential energy of the object, then the work is going to just change the kinetic energy of the object. If we're not changing the kinetic energy of the object, then it's just going to be changing the potential energy. And so here's two scenarios for you. So work, if we have an object that is initially at rest, and I apply a horizontal force on it equal to F, and that horizontal force is applied over some distance d. Later on, over this distance d, this force, which has been applied for distance d, now has created some velocity which is not equal to 0. And so the result is, because I didn't increase the gravitational potential energy, the work here increased the kinetic energy. Right? Because I had a force that was applied over some distance. That force created an acceleration. That acceleration then created some velocity, and that velocity is now non-zero. Take that in contrast to an object over here, initially at a height of 0. If I apply a vertical force, which is equal in magnitude to its mass times gravity, then by the time I get up to here, it still has 0 velocity, right? If it's on the ground here, it has 0 velocity. It still has 0 velocity, but now its height is not equal to 0. And so in this case, when we exerted our force in the opposite direction of gravity, we had work increase my gravitational potential energy. And so on the left, work is increasing my kinetic energy. On the right, work is increasing my gravitational potential energy. And so sometimes work will increase our energy in different ways. So work will always increase energy. Depending on what kind of situation it is, work will either increase our kinetic energy, or it could increase our gravitational potential energy, or it could increase both, right? If this force over here was not equal to mg, but was in fact greater than mg, then that would mean that I would increase both the kinetic energy and the gravitational potential energy. So the amount of work done is equal to the change in energy. The amount of work done is exactly equal to the change in energy. So work done is equal to the change in total energy. Work done is equal to the change in total energy. So if my change in energy is just in kinetic, then we have the work done for kinetic equal to my change in kinetic energy. If my work done is in potential energy only, like say lifting up an object, then my work done is equal to the change in gravitational potential energy. Okay? Either way, we have a change in energy. And so the key is to understand that the amount of work that we do is exactly equal to our change in energy, regardless of the type. So let's take a look. Here's a car that crashes into a tree. No one's hurt. Airbags are deployed. Everybody has insurance. Awesome. Nobody's, no bad things happen. And this car is initially moving at 12 meters per second. It hits the tree. It's now traveling at 0 meters per second. It has a mass of 2,000 kilograms. And I want to know all of these questions here. So go ahead and figure out questions 1 and 2 for now. So the change in kinetic energy and the amount of work done as the front of the car crashes into the tree. Go ahead, pause. And welcome back. So our change in kinetic energy, delta K, is going to be equal to K final minus K initial. K final, that's 1/2 m times V final squared minus 1/2 m times V initial squared. So the result is that our change is negative 1.44 times 10 to the 5th joules. So as you plug in all those values, you get 1.44 times 10 to the 5th joules. It's negative because we started with some amount of energy and we finished with no energy. Excuse me. So if my change in energy was negative 1.44 times 10 to the 5th joules, remember from back here we said that the amount of work done in general is equal to our change in total energy. The amount of work done is in general equal to our change in total energy. And so if this is how much our change in kinetic energy is, we didn't change our energy gravitationally, so our work done then is equal to negative 1.44 times 10 to the 5th joules. Negative 1.44 times 10 to the 5th joules. And so then we've got this final question of finding the size of the force that pushed in the front of the car by 50 centimeters. So if we take a look, we know that the work done was equal to the change in kinetic energy. And so mathematically, that's equal to 1/2 m times V final squared minus 1/2 m times V initial squared. And that's equal to work. Now, this side over here, V final minus V initial, and those squared, that kind of looks something like an equation that we've seen before that has V finals and V initials both squared. And so I can go through and say that work, and this is all just work equals all of this stuff. So if I said that this was 1/2 m times V final squared minus 1/2 m times V initial squared, what I would get is the following. So if I factor out an m from here, I've got m times 1/2 V final squared minus 1/2 V initial squared. And if you remember the VF squared equation that I was talking about, it was VF squared equals VO squared plus 2AD. Since we're looking for a force, we want to somehow get an A in here, right? Because m times A gives us a force. So if I solve this for VF squared minus VO squared, that's going to equal 2AD. And so then if I actually solve it for 1/2 VF squared minus minus VO squared, that's equal to A times D. And the result is that this entire piece right here is equal to A times D. And what do we have left over? This is equal to M. So far I've got work equals MAD, mass times acceleration times distance, but we should remember that MA is force. And so the result is that for a force that's applied parallel or anti-parallel to the motion, the amount of work done by that force is equal to force times the distance over which that force acts. So I'll say that again. For a force that's applied either parallel or anti-parallel to an object's motion, the amount of work that's done on that object is equal to the force exerted times the distance that the force is exerted. And so if we know that this, in this case, is negative 1.44 times 10 to the 5th joules, and we know that our distance is 50 centimeters, which is 0.5 meters, the result is that our force is equal to negative 1.44 times 10 to the 5th divided by 0.5 meters. And the result is that our force is equal to 2.88 times 10 to the 5th joules. Newtons, not joules. Converted into pounds, that's approximately 64,000 pounds of pressure. or 1,000 pounds of force. That is a lot of force. Okay, and so let's recap then. We've got 3 new equations that we have come up with and 2 new concepts. The first equation is that our kinetic energy is 1/2 mv squared. The second equation is that gravitational potential energy is equal to mgh. The third kind of equation, the third equation is work equals force times distance. I'm going to add in this cosine of theta, and we'll talk about it in next class. But for forces that are parallel or anti-parallel, don't worry about the cosine theta. We also have 2 concepts. The first concept is that our energy initial will always be equal to our energy final in the presence, or in the absence rather, of friction. And the second concept is that the work done by any force is equal to our total change in energy. The work done by any force is equal to our total change in energy. That's it for this video. Sorry it was so long, but I think there's a lot of really good information here, and we'll see you next time in class.